Hi, good morning, everyone. I'm Dr. Christofidou. I'm a lecturer in metallurgy at the University of Sheffield. And today I'm actually presenting some work that was done a little while ago while I was still a postdoc at the University of Cambridge. So the work is a big collaboration between the University of Cambridge and Rolls-Royce PLC. And I would like to start by thanking all of the co-authors in the team led by Professor Howard Stone, working in collaboration with the Rolls-Royce additive manufacturing teams. So the topic of the talk today is looking at the microstructural control and optimization of the microstructure of Haynes 22 manufactured through laser powder bed fusion. And I wanted to start with a little bit of motivation. We've heard quite a lot of this already this morning by Professor Pollock, but I thought I'll run through a little bit of it again. So the motivation of the work was looking at the jet engine and aerospace applications of nickel-based superalloys and where we can find uses for additive manufacturing. And as we know, there's a continuous demand for improving efficiencies, reducing fuel burn or improving our fuel burn before we even start discussing alternative fuels, such as sustainable aviation fuels or hydrogen. And as a way to achieve this, there's loads of different motivations, including the geared turbofans and the like that some companies are looking into. But a more readily achievable way is to reduce the core of the engine and create a smaller, faster rotating core, right? So we increase the temperatures in the engine itself within the core, but we also increase the stresses that the core is experiencing. As a result, we need to look at the materials that we're using because those materials need to withstand both higher temperatures and higher stresses. And we also can look at the component designs because advanced manufacturing offers us that capability to change our component geometries, introduce more complex cooling channels and the like, so that we can cope with the increased demands in service. And if we look at a quick cross-section of the jet engine and where the different materials are being used, this is about 20 years old, and you'll see at the front of the engine, we have quite a lot of titanium. It's nice and light, we like it, but it doesn't have the temperature capability. So as we move through the engine to the higher temperatures, we increase the amount of nickel that we use. So the new engines, the new concepts of engines that we're looking now, have that nickel-based superalloy sort of red section coming further and further front, right, as the temperatures are increasing. And that is both good and bad. It means we need to completely change the makeup of the engine, it makes it a lot heavier. We're looking at increasingly more complex chemistries of nickel-based superalloys. So if we can use manufacturing to help us semi-artificially reduce those temperatures in the component, we can create a better sort of makeup for the engine in terms of lightweighting and the complexity of the chemistries that we're looking at. So very briefly, nickel-based superalloys, if you're not familiar, we primarily consist of two phases. The gamma phase matrix, which is an FCC nickel-based solid solution. We like it, it's nice and ductile. It has low rates of self-diffusion, so its creep is quite good. It has good solubility for lots of different elements, so we can tailor it quite nicely. But we can supercharge those properties by using the precipitation of the L12 gamma prime phase, which is a nickel-3 aluminium ordered intermetallic. And using that, we can increase the temperature capability and mechanical performance significantly. Now, what does that mean in terms of additive in aerospace propulsion? As I said, if we can use advanced manufacturing, we can access much more complex geometries. We can introduce cooling, much more complex cooling that we were able to with alternative methods. We can reduce the number of parts that we need and the joining and fastening, and we can reduce the lead times for component manufacturing since we don't need as much post-processing. But when we start thinking about the material that we're using in that, nickel-based superalloys are particularly problematic in that the higher the volume fraction of the gamma prime, which is the strengthening precipitate, so what we use for the mechanical performance and the temperature capability, the worse it is for additive manufacturing. So we have increased propensity towards cracking, and we find difficulties in controlling the microstructure the higher the gamma prime content as well. But post-processing is necessary to tailor the mechanical properties and modify those non-equilibrium structures as well. So there's a lot of challenges still, and the more materials we look at, the more challenging it gets. So in this particular work, we were looking at Haynes 282. This was an alloy that was developed for a combination of good creep resistance, thermal stability, and weldability for applications in a range of temperatures from 650 to about 930. And one of the reasons that we were interested in Haynes 282 is that it has a fairly large range of temperature capabilities at a fairly controlled and low fraction of gamma prime. So our gamma prime fraction is controlled to about 20 to 30%, and the microstructure is optimized through heat treatment. So traditional cast and wrought Haynes 282 uses a super solvent homogenization at about 1150 degrees Celsius, followed by 1010 degrees Celsius for 2 hours to precipitate the M23C6 carbides at the grain boundaries, and then 788 degrees for 8 hours to optimize the gamma prime distribution. So quite a complex post-processing heat treatment for a nickel-based superalloy. And the microstructure is actually quite stable. So we don't see the formation of deleterious phases like TCP phases or excessive growth of the gamma prime either at temperatures over 870. And really looking at the composition of the material, it's quite remarkable that it doesn't do that. When I first looked at it, I was convinced it was going to be horrendous for stability, but it isn't. It's beautiful. So in terms of additive manufacturing of this material, at the time we were doing this study, there was very little on the additive manufacturing of Haynes 282. It was primarily just a few studies using electron beam melting. Since then, there's been a few more, but I'm bound by industrial clearance processes, which means that I can't update slides very easily. So we're sticking to the few studies that were available at the time. And one of the key things that was identified was that the microstructures, but particularly the carbide distributions, were quite different from the cast and wrought to the additively manufactured component. So one of the key things was the MC carbide and the M23C6 and where and how it precipitates through the material. So in this study that I've included here by Christofidou-Microstructural, we've got a couple of different heat treatments. On the left is the two-step aging that's recommended by Haynes, which results in some large titanium-rich MC carbides with M23C6 at the grain boundaries. And what they were looking at was how they can influence that or achieve that without having the multiple steps. And what they found was actually they can just create a very similar microstructure with just 4 hours at 800 degrees Celsius. So that suddenly changes a lot of the dynamics of our microstructural optimization. So that gives us an opportunity to actually tailor the microstructures using post-deposition operations to obtain optimal mechanical properties, rather than just looking at the build alone. So what we did, we built a bunch of Haynes 282 samples using an EOS M280 instrument from virgin powder up to sizes of 45 microns. The build parameters were kept constant for the samples, but I can't share them. Even if I wanted to, I don't actually know them. I was bound by this confidentiality again. So we had a few different coupons. So we built 30 by 30 millimeter squares by 1 millimeter thick samples that we did the microstructural characterization on. And then we had small bow tie specimens that had a 1 by 1 millimeter squared cross section by 20 millimeters sort of gauge length. So we're looking at equivalent microstructures in terms of thickness to what we're testing. We did some DSE analysis to help us identify some of the key transition temperatures for the material and then design our heat treatments from there. So the liquidus of the material was about 1390, the solidus 1270, and the gamma prime solvus was at about 1000 degrees Celsius, which helps just pinpoint a few things. So the first couple of heat treatments were what we call the industrial ones. So we sandblasted the samples. This seems to be a standard thing for the surface finish for this particular application. And then we had the 50 degrees Celsius for 1 hour solution heat treatment or homogenization heat treatment, followed, so the first heat treatment is just that, just the solution, and then we have the two-step aging attached to that for the second one. The rest of the heat treatments were lab-based ones, so we encapsulated all the samples in quartz tubes, and we heat treated them in lab furnaces under a range of different conditions. So you'll notice that we have a much higher solution heat treatment, and we played around a little bit with the solution heat treatment, and I'll come to that in a second why. The other thing that we did was look at the intermediate aging step. So the current Haynes 282 recommended for cast and wrought is super solvus, super gamma prime solvus, whereas we looked at a couple of heat treatments sub-solvus to see what that would do to the material and its properties. And then we kept the gamma prime optimization to 788, just because that seems to work quite well anyway. We did some microstructural characterization after each of these steps, and we did the mechanical testing on an electrothermal mechanical testing machine. Effectively, we tested tensile at 900 degrees Celsius at 10 to the -5 strain rates, and we did some creep testing that we tried to get about 100 hours lifetime from, so we were using data from the existing literature. So that was 900 degrees Celsius at 120 MPa. So looking at the microstructure to begin with, if we concentrate on the first row of microstructures, the first thing to notice is that the conventional raw heat treatment doesn't actually lead to recrystallization. We keep the highly misoriented cellular structures that we might expect from the deposition. We don't see much difference from the as deposited to the solution heat treated. We can start seeing the precipitation of the M6C carbide, just tiny little black dots at the grain boundaries. And then following the two-step aging, what we see is M6C, the bright phase there along the grain boundaries is a molybdenum-rich M6C carbide. And in between that, we've got M23C6. Importantly, we don't see any MC carbides, so no MC or carbonitrides of any sort, monocarbonitrides of any sort, which is quite common in both the E-beam material and the wrought material. The second thing to notice is the recrystallization. So as I said, in the traditional 1150 degrees Celsius homogenization, we don't get recrystallization. So we played around with the temperatures for the recrystallization to see when we would actually induce it, because that was quite an important factor for us. And what we found was that recrystallization needed an hour at 1250 or a couple of hours at 1240. And we looked at different compositions for that, with different durations for that as well. So the main thing was that we were looking at recrystallized material before we were looking at the intergranular microstructures. So I'm going to ignore the first two that didn't recrystallize for the rest of the talk. I'm just going to concentrate on the microstructures of the rest. So the first heat treatment C, which was basically recrystallized, the two-step aging as normal, and then gas fan quench, so quick quenching from temperature. You can see a very, very fine structure for the gamma prime, and then we have carbides along the grain boundaries. So that was the one that was mainly different, just because it was the only one that we quickly cooled. Everything else has equivalent furnace cools. So we see the carbides precipitating in very similar structures. So we don't see a huge difference in morphology for the carbide species, but the carbide species are M23C6 and M6C. We don't see anything else coming out in any of them. The key difference that we see is the tertiary gamma prime. So if you look at probably this third one here and the fourth one there, you can see around the gray boundary, we have the tertiary gamma prime coming out. Yeah. So the only two heat treatment conditions that we didn't have that were the ones that we had the second heat treatment stage subsolvers to the gamma prime. Yeah. So you can see in this one, for example, you can see growing of the gamma prime around the gray boundary, but a distinct lack of tertiary gamma prime coming out. And the reason we wanted to have that was later on when we were testing the creep to see if that had any effect to the properties. So tensile properties at 900 degrees Celsius, apart from the one that we quickly cooled, which gave us a much finer gamma prime distribution, everything else is within error. So everything is equivalent. The elongation, you can ignore. The electrothermomechanical testing is very bad for elongation. The main thing I included it for is just to say it's not brittle. So it has quite a fair amount of ductility after all of these heat treatments. So there isn't a massive debit on the ductility even at temperature. Now, the more interesting results came from the creep. So the tensile, we didn't really see any changes in the microstructure. We weren't expecting massive differences in the tensile. That was sort of logical. The creep, we were expecting to see a lot more differences, but they didn't really correlate very well. So we didn't manage to get good data from some of the conditions. So condition C here looks okay, but it doesn't stick out. So the gamma prime distribution didn't seem to influence necessarily the creep performance. So just the finer gamma prime seems to be equivalent to the larger gamma prime as well. Condition C, D, and H. So the blue and green lines in there all are about the same. And it kind of shows you the variation in the method that we use to test the creep. We've got about 30% variation in the methodology itself. So we get lives of 70 to 130 hours, right? We were aiming for about 100 hours. So we are within that range, which is great. The two ones that stick out considerably as being very, very bad are E and G. Yeah, and they had creep lives of 30 hours. So even with a 30% issue, we wouldn't get much higher than that, or even close to what we were looking at. And the post-mortem analysis that we did on the fracture surfaces didn't actually show any oxidation to suggest that that was the reason why we were getting the bad creep performance. And there wasn't any correlation in the end with the tertiary gamma prime at the grain boundaries. So exploring a little bit more the literature, it seems that some of the key factors for the creep performance of Haynes 282 is actually down to the molybdenum content in the gamma phase. And because we've changed the carbide precipitation sequences, we're now locking quite a lot of molybdenum in the M6C carbides, right? So there's not as much of it in the matrix. And even 1 weight % change in the molybdenum content is causing a huge change in the creep properties. So we think that's the key reason that we're seeing that massive difference in the creep performance. We also did a quick long duration stability study that didn't really show anything. We just changed the morphology of the carbides and confirming that they stay as M6C and M23C6, nothing else. The gamma prime grew a little bit, but up to about 150 to 200 microns. So I'm aware I've run out of time, so I'm going to just leave those up there and take any questions if you have them. Thank you.